These are notes for geometry section 8.1, the geometric mean. And I am pre-recording this because I will be gone on the day that you do these notes. And so as you need to pause things to see or to write things down, you can do that, and I will just kind of move forward. So this is the title page, 8.1, Geometric Mean, and the essential question, can you find the geometric mean and solve problems involving right triangles? And so if you need to pause this to write that down, go right ahead, and I will just be moving on. There are several handouts for this section, so hopefully you have gotten those, and if not, you can also pause this now to get those handouts. There are two handouts for this section 8.1. One with the key concepts and theorems on it, and one for the problems that we'll be doing in class. So again, pause that if you need to. Here is the key terms page. And I'll read this to you, and you can write it, and if you need to pause it, then you can. When the means of a proportion are the same number, that number is called the geometric mean of the extremes. So when you write this proportion, a over x equals x over b, and I'll maybe just write it myself, a over x equals x over b. Notice the very first thing I wrote was the a, and the very last thing I wrote was the B. Those are called the extremes because they're kind of the first and last thing that you write. And then the middle things that you write are those two X's, and so they are called the means because they're kind of in the middle. And so again, if you need to look at that, go ahead as you go, and go ahead and pause that. Otherwise, I'm going to move on. We're going to move on now to the key terms page, and you'll see the key concept of the geometric mean. When you looked at that proportion that you wrote in your key terms, if you cross multiply, and I'll just, because I'm not here, it's hard for me to point, I'll just read this to you. The geometric mean of two positive numbers, a and b, is a number x such that a over x equals x over b. So then when we cross multiply, if I have, and I'll just rewrite it, a over x equals x over b, when I cross multiply, I get x squared equals a times b, and then I'm going to square root both sides, and since we're talking lengths, usually we use the positive square root, so x equals the square root of ab. And so that is very important in this section. And so the geometric mean of two positive numbers a and b is x, where x equals the square root of ab. And so the geometric mean of 9 and 4 is 6, because 6 equals the square root of 9 times 4. We just did a little extra section on simplifying radicals, and we'll be using radicals in this chapter, so that's a good reminder for us. Theorem 8.1, I will read this one to you as well, and you'll notice that they've kind of pulled apart some of these triangles to be able to see them easier. The red and the blue are just pieces from that black picture. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. And so we'll highlight here, if altitude drawn to the hypotenuse of a right triangle, then two triangles formed similar to the original triangle and each other. So here's kind of what we get is that in this picture, triangle ACB, and if I kind of think of that as the long leg and the short leg, it's not always super easy to think about that, but if I name that first triangle, triangle ACB, and I've traced it kind of the long leg and then the short leg, then I can say that is similar to, and if I trace long leg and short leg of the left triangle, then I can go ADC. That would be triangle ADC. D, C. And I'm not doing the same order as the book authors there, but that's okay. And then if I take that little triangle on the right side and I trace kind of the long leg and the short leg, I get triangle CDB. And so those are the triangles that are similar to each other. And of course, if we put it in the order, you know, A, B, C, then it would be ACD, and then it would be CBD. And those are the orders that the book author use there for that one. So it's a little tricky sometimes to find those legs, but if you can identify like a long leg and a short leg and then a hypotenuse, sometimes it'll be easier for you to kind of find those. And you do need to find those. The book authors kind of pulled them apart as they looked at that. Then the reason we want to kind of know that is because then since these triangles are similar, we get ratios of the sides that are in proportion or equal to each other. And so we get a bunch of geometric means because some of these values are repeated. So this is right triangle geometric mean theorems. And again, I'll read this since I'm not here, and usually I have you guys read it. The geometric mean or altitude theorem, the altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of this altitude is the geometric mean between the lengths of the two segments. Now, that's good and important. It's a little hard to kind of say what is happening there, but essentially the geometric mean altitude theorem is, it says that the altitude to the hypotenuse has a length that is the geometric mean between the lengths of the two segments that are kind of cut. The length of the altitude is the geometric mean. And so the big thing here is this h equals the square root of xy. And so on this picture, maybe kind of just give yourself a little indicator. So it's this h that is that altitude there, and it's the geometric mean of that x and y. So h equals the square root of xy. Try to keep in mind that altitude comes right down from that main right angle of the biggest triangle, and you use the two little pieces that are close to that as you go. Then there's a leg theorem as well, and so these legs are going to be those outer sides of the big right triangle, so that little b, which is segment AC, and the little a, which is segment CB. So this is the geometric leg theorem. First, I'll read it. The altitude drawn to the hypotenuse of a right triangle separates the hypotenuse into two segments. The length of a leg of this triangle is the geometric mean between the length of the hypotenuse, that whole hypotenuse, and the segment of the hypotenuse adjacent to that leg. So this is the length of a leg of this triangle, and kind of having this situation is the geometric mean between the hypotenuse, which is the long hypotenuse all the way across the bottom, which is segment AB, or listed as that little c, and the segment of the hypotenuse adjacent to that leg. So, and I'm going to color code these a little bit, so if you do have two colors, that might be helpful. So that means this little leg B over here is equal to the product of the little piece of the hypotenuse on the bottom that is close to it and that whole hypotenuse. So little b equals the square root of xc. And then I'll use a different color. Little a is equal to the geometric mean of the little piece close to it and that whole hypotenuse. So little a equals the square root of yc. So if I can kind of see these all on the slide at the same time, it's a little bit hard. But just notice I'm going to kind of revisit that. This top one, if you know that H, it's the geometric mean of the two pieces. So if it comes down through the middle of the triangle, then the two little pieces are the X and Y. But if you're using one of the original legs of the big triangle here, then that leg is the geometric mean of the little piece of the hypotenuse close to it and that whole hypotenuse, and then this other leg, which is over here, is equal to that piece close to it and then times that whole hypotenuse as we go. So if you can kind of figure out a little like routine for yourself, that would be awesome. If not, you can always kind of match the sides that go together, and that's really how we get the geometric mean as we look at this. And so I'll highlight this in yellow a minute. If I kind of look at this one and I put C over A, so C is the hypotenuse of the big triangle and A is the leg of the big triangle. So when I write that ratio, then A is also the hypotenuse of this triangle that's right here. So that's how you're getting the hypotenuse of that triangle. And then Y is the kind of matching leg of that triangle. So it's hypotenuse over leg, hypotenuse over leg. And again, you know, if you forget what the actual ratios are there, you can kind of use that as well. And then at the bottom of this handout, and I used to do this as kind of a separate handout, but at the bottom of this handout, I have just some little reminders to kind of help you figure out how to do these problems as you go. So we'll kind of fill in the blanks here. Notice that if we want that y part, this y is the geometric mean of the two pieces that are close to it. So y is equal to the square root of zn, square root of zn. And then over here, this m, so just using some different letters, this m is equal to the square root of the piece of the hypotenuse close to it and the whole hypotenuse. So it's equal to the square root of z times t. And then the last one is this side x over here, this leg x, and that leg x is equal to the square root of the piece of the hypotenuse close to it, which is n, and then times that whole hypotenuse on the bottom there. So x equals the square root of nt. For that one. Then over here, I just have this little reminder. So when you look at that bottom, and I'll use the magic pen this time so that it'll erase itself. If you look at that bottom, this segment PR, which is that whole length right there, it's made out of these two little pieces, PS and SR, and we know that in order to, by the segment addition postulate, in order to get the length of the whole thing, we add the two little pieces. So that whole thing is also labeled as T here, and so T is that whole thing, and that's equal to Z, this piece right here, plus N, this piece right there. And so T equals Z plus N. So sometimes you might be in a situation where you think you don't have enough information, but I'm just going to remind you that if we do know that T equals Z plus N, then Z, in order to get that little piece Z, we can take T minus N. So that whole thing minus N is equal to Z. And if we need to find N, it's T, the whole thing, minus z. So just some little adding and subtracting things that we already know, but just to kind of remind us as we go through this. You probably want to have this piece of the handout close to you as we go through some of these problems in this lesson. So now there's just another piece of that. Now we're going to just do some geometric mean problems. So number one is to find the geometric mean between 2 and 50. So this is just what is the geometric mean? And so the geometric mean, I'm just going to say x equals the square root of 2 times 50. So x equals the square root of 100. And so x equals 10. And again, we will put those in simple radical form, and we just kind of got finished a little review of that, so that should be helpful to you as you go. Then our next problem is to write a similarity statement identifying the 3 similar triangles in the figure. So when I look at this one, I look for these problems to kind of, what is the relationship, or how am I going to find these 3 triangles that I need as I go through this? So I would identify the big triangle, which is that whole picture. There's 3 triangles there, and I like to kind of try to look for like a short leg and a long leg. So I would look at this right triangle, and that's triangle EFG, and I'm going to kind of trace it short leg and long leg. So I'm going to say triangle EFG is that first triangle. Then I need another one where I'm going to go kind of short leg, long leg. So on this left triangle, and I'll just trace it right here so I know what one I'm talking about. On that left triangle, I'm going to go short leg, long leg. So if I do that, I'm going to go from E to H to F, E to H to F. And so that's triangle EHF. And going kind of that short leg, long leg. And then for the last one, again, this is the triangle that I'm looking for right here. So I'll kind of trace it a couple times so you can see it. And then if I go short leg and then long leg, that is FHG. So triangle FHG. And so those are the triangles, and they are all similar to each other. So I'll put my little is similar to symbols in between them as we go. Then I will just point out, I have another slide just to show you, and the book authors sketched them and kind of reoriented them so that the corresponding angles and sides are in the same position as the original triangle. And if that's helpful to you, it also does that in the textbook. You can kind of look at that as well. Then a big topic here is finding missing lengths when we have a right triangle and an altitude, making that picture into 3 right triangles. And so when we look at this, we want to kind of remember these geometric means. And I'm just going to remind myself that, and I'll write with the magic pen a minute so that it kind of just erases itself. And if this piece is 6 and this piece is 24, so 6 is there and 24, then I know that from there to there is 6 plus 24. So just a reminder that I can find that length as I go, and I am going to need that length as well. So other things just to recognize, here's the main right angle. So this side is the hypotenuse of the whole triangle. This is that altitude that's in between there, and that's going to be the geometric mean of the 2 pieces that are kind of close by that it breaks that big hypotenuse into. And then let me wait until that all disappears. And then this leg of the entire big triangle is equal to the geometric mean of the little piece close to it and that whole hypotenuse. And so, if we kind of flip it over, then the same thing happens for the other leg of the big triangle. So here's the leg of the big triangle. It's equal to the geometric mean of the piece close to it and that whole hypotenuse as we go. So I just wanted to visit about some of those pieces before we kind of go on to kind of figuring things out. So I am going to right now just draw in a line here, and that means and that I'm going to find that whole length. So JM is 6, ML is 24. So JL, that whole hypotenuse, is 6 plus 24, which is 30 as we go. And I will color code my problems just to kind of make it a little bit easier. So this altitude here, E, is the geometric mean of the two pieces close to it, or that it divides that big hypotenuse into. So E is equal to the square root of 6 times 24. So E is equal to the square root of 6 times 24 is 144. That's a perfect square, so E equals 12. It won't always be a perfect square. We can put it in simple radical form if we need to. We can also put it as a decimal if needed as well. So then the next one that we're going to look at is one of these legs. I'm going to just pick D next. And I like to do that middle one first if I can. And then D, I'll trace that. That's the geometric mean of the little piece close to it and that whole hypotenuse. So D equals the square root of 6, the little piece, segment JM, and times the whole hypotenuse, which is 30 as we go through that. So D is the square root of 180. And then we'll use take a minute here and just get that in simple radical form. So 180, 2 goes in there 90 times, 2 goes into there 45 times, 3 must go into there 5 times, 3 goes into there 5 times. So D is equal to the square root of 2 squared times 3 squared times 5. And just a reminder, the 2 squared and the 3 squared are perfect squares. So D equals the square root of 2 squared times the square root of 3 squared times the square root of 5. And so in simple radical form, the square root of 2 squared is 2, the square root of 3 squared is 3, and then times the square root of 5. So D equals 6, the square root of 5. We might just be asked for a decimal approximation of that as well. And so if we are asked for that, really up at this point where D equaled the square root of 180, we could put that in our calculator as well. So this one, if we needed the decimal, D is approximately 13.4. Sometimes we'll have to use an answer to find another answer, so sometimes just finding that is a good idea as well in simple radical form. I'm going to slide this down just to be able to see that last part I have to get, C. C is this leg, and that is equal to the geometric mean, or that is the geometric mean of the piece of the hypotenuse close to it and that whole hypotenuse again. So this one, C, is equal to the square root of 24 times 30. And then this is the square root of, C equals the square root of, well, 24 times 30 is 0, that's 12, 7. So that's 720. And so I'm going to write the prime factorization of that. Maybe I'll just use my space above here. So 720, 2 goes into there, 360. 2 goes into there, 180. 2 goes into there. We did this prime factorization already, but that's okay. 2 goes into there 90 times. 2 goes into there 45 times. 3 goes into there 15 times. 3 goes into there 5 times. So the prime factorization for this one is the square root of 2 to the 4th times 3 squared times 5. And so this is the square root of 2 to the 4th times the square root of 3 squared times the square root of 5. And so the square root of 2 to the 4th is 2 squared. And you know, if you kind of figured that out, 2 times 2 is 4, times 2 is 8, times 2 is 16. So that's the square root of 16, which is 4, and that's what we're going to get, times the square root of 3 squared, which is 3, times the square root of 5. And so that's 4 times 3, the square root of 5, and so that's 12, the square root of 5. So little c is equal to 12, the square root of 5. And I'll maybe slide that up a little bit for you to see. And if you needed a decimal approximation of that, it would be about 26.8. So C is approximately 26.8 if we need that as we go. So these are kind of challenging problems, but they're good for us to look at. And if I'm doing most of this lesson all in one sitting. If you don't get done with everything on one day, you can kind of just start it up where you left off. And so I think I think I will do this problem in this recording, and then you'll just have the handout of problems to do as you complete this. So this is Mrs. Ausbach is making a kite for her son. She has to arrange two support rods so that they are perpendicular. The shorter rod is 27 inches long. If she has to place the short rod 7.25 inches from one end of the long rod in order to form two right angles with the kite fabric, what is the length of the long rod as you look at that? So I'm actually just going to kind of make some observations here. I'll draw with the magic pen so that, you know, it kind of erases itself. So notice this is a big right triangle right there, and that down here at the bottom, that's the same big right triangle as we kind of look at those. So we can just kind of pick one of these right triangles to kind of look at and figure things out for. Also, if these two pieces right here and right here are the same length, they have this, then I can take that 27 and divide it by 2, and that'll be that length and that length. So I'll have that length as I go. I know this is 7.25. That's that little piece that's right there. And I want the length of this whole long rod as we get that. So really, I'm going to start by trying to find that little piece. And then if I can find that little piece, I'll have everything that I need. So let's take a minute. I'm going to just retrace this piece of the triangle or of the kite. And so that's going to be my right triangle. And this is a right triangle, that's a right triangle, excuse me. 27 divided by 2 is 13.5 inches. So I know this piece right here is 13.5 inches. I already know that this piece right here is 7.25 inches, just from there to there. And then, like I said, I'm going to call this piece X from there to there, because this 13.5, which goes up and down here, is the geometric mean of those two pieces. So if I set that up, I can find X, and then I need the whole length of the long rod, but I can just add 7.5 or 7.25 and x, and I'll get that long rod. So my geometric mean is 13.5, and that's equal to the square root of 7.25 times x. And then I'm just going to remind you that for this problem, we're going to square both sides to get rid of that radical. And 13.5 squared is 182.25. And then the square root of 7.25x squared is just 7.25x. And then to get x alone, we're going to divide by 7.25 on both sides. And then we get 25.14 is equal to approximately equal to x. So we are just gonna, kind of get what we get there. It is equal to x. I'll just keep it equal to x. And so then really we were asked for this long rod, which is that distance along there. So the long rod of the kite is 7.25 plus 25.14, and so that is 32.39 inches. Now, I'm going to stop this recording. The next thing you're going to do is some handout problems, and then you might do those tomorrow, or it might be the second day that I'm gone, and then you will have some time to maybe work on some of these homeworks as well. So there is that, and you'll be able to check those handout problems, but I won't have a recording of